Here we have, suppose, equation of the form px d2y dx2. I'm taking the standard form of second order equation qx dy dx plus rx y equals to 0. Now see, previously what we considered, this p function, q function and r, these are constant term, but here see, as you can see, px, qx and rx, these are function of x, okay, these are function of x. So here you have differential equation with variable coefficient. So here make this equation number 1. Okay, now this one, equation 1, can be expressed as d2y dx2 plus qx px dy dx plus rx px y equals to 0. Here I considered homogeneous form. So now see, here this function, this qx by px, this rational function, and here rx by px, okay, these two functions, they play a very vital role for the nature of this equation. Okay, now see, here we have few terms like ordinary point, then singular point in the context of differential equation with variable coefficient. To be very specified, it is second order equation. Okay, now what is this ordinary point? Suppose a point x naught, it is said to be ordinary point if this p of x naught, it is not equals to 0. P of x naught, it is not equals to 0. What actually it means? See, p of x naught, if this one, it is not equal with 0, then what you have, this term qx by px and rx by px, both are analytic, okay, at x naught. If they are analytic, see, these are nothing but some rational function where this numerator and denominator, they are individually some polynomials. So obviously this qx, rx as well as this px, all will be are analytic at x naught. Analytic at x naught means it is differentiable basically. Okay, it is basically it is differentiable for any neighborhood of x naught. Okay, so this function px, qx and rx, these are analytic at x naught. Okay, so these are analytic at x naught. This is the condition, and because of you have that p of x naught, it is not equal with 0. That means if you take the limit of this qx by px as x tends to x naught, you will get some finite value, as well as this limit rx by px, if you take the limit as x tends to x naught, you will get some finite value. Okay, so the basic thing is this one. For all those points, if you are getting that p of x naught not equals to 0, then immediately x naught is ordinary point. Now see, the next one, it is singular point. So singular point, here already stated that it has two categories. One is regular singular point, another is irregular singular point. Okay, so for the case of regular singular point, what you have, see, this coefficient. For the case of regular singular point, limit of x tends to x0, x minus x0, this qx by px, and limit x tends to x0, x minus x0 square, rx by px, both exist finitely. Exist finitely means if you find the limit, you will get some finite value. That's the idea. okay, then you have the regular singular point. If it is not regular singular point, then you have the case of this one, irregular singular point. That means for irregular singular point, if either of these two limits, at least if both, then obviously we have irregular. Okay, if either of these two limits fail to exist or gives infinite value, then immediately what we have, irregular singular point. Okay, irregular singular point. So this is the idea. Now here we can take few example. Through that we'll try to understand, or we are going to validate this concept of regular point. Okay, that means the ordinary point, a regular singular point. So we can take one or two question here. So here if I take suppose one problem, that is, say for example, 1 minus x square d2y dx2 minus 2x, that we'll see later on. This is a standard form which is known as legendary equation. So n into n plus 1 y equals to 0. So for this equation, just see here px, it is 1 minus x square. Here qx, it is minus 2x, and rx, it is n into n plus 1. So here if you see x equals to 0, if you are taking x equals to 0, see p of 0, it is, we are getting 1, so which is not equal with 0. So immediately you can claim x equals to 0 is an ordinary point for, suppose this was equation number 2. So equation number 2, this is equation number 2 for 2. Okay, similarly see, you take any other point apart from x equals to plus minus 1. See, if you are taking x equals to 1, so p of 1, the value it is 0. Okay, similarly p of minus 1, the value it is 0. So immediately you can claim that x equals to plus minus 1 is singular point. Okay, singular point. So for x equals to 1, suppose at x equals to 1, you want to check whether it is regular singular point or not. So in that case, limit x tends to 1, x minus 1, that quantity, that is qx by px, you need to find this quantity, that is limit as x tends to 1, x minus 1 qx. What is that qx? Minus 2x by 1 minus x square. So you can easily calculate this limit, and it will be limit as x tends to 1 minus 2x by 1 plus x. So the value should be minus 1. Similarly, if you want to check this one, limit as x tends to 1, x minus 1 square rx by px. If you want to find this, there is limit x tends to 1, x minus 1 square, here n into n plus 1 by 1 minus x square. So the value, it should be limit as x tends to 1, x minus, here you will be getting x minus 1, n into n plus 1, here you will be getting obviously 1 plus x, and you will get 1 minus sign as well. Correct. So here also you are getting, I guess, 0 is the value. Okay, so both are finite. Okay, so you can claim that x equals to 1 is regular singular point. Okay, regular singular point. Similarly, you can check that x equals to minus 1 is also a regular singular point. Okay, So this is how we can check whether we have ordinary point or singular point. Okay, one particular point can be given and check whether it is ordinary point or singular point. If singular, then which type. If it is not regular, suppose here you are getting infinite, out of these two limits, if at least one you are getting infinite, so immediately you claim it is irregular singular point. Okay, so this is one basic understanding from this second order differential equation with variable coefficient. Sturm-Liouville equation, or it is known as SLP, Sturm-Liouville problem. Okay, so in that case, the general form of SLP, that is Sturm-Liouville problem, it is given by ddx of px dy dx, that already we studied in our class, plus lambda omega x minus qx is equal with 0. Okay, so this already we have studied this idea. Okay, now see here there are few specific conditions. That means first thing, it should be given that range, it should be clearly mentioned in the problem. That means what is the x value, from where to where it is lying, this should be given in the question. Okay, second thing, here you can see this is nothing but a second order equation, but it is written in a more compact form. Now this part of this equation, see ddx of px dy dx minus qx y plus lambda omega x y. Okay, this part, it is actually one important operator which is known as self adjoint operator. It has its own importance, the self adjoint operator. So the self adjoint operator, what actually it is, see, let me write this self adjoint operator for you. So that is given by L of y minus ddx of px dy dx plus qx y. This is the self adjoint operator, and here you can see exactly the same thing with a little variation in minus sign. Okay, that means minus ly, it is present here. Okay, so this equation can be expressed like this, that is minus ly lambda omega x y equals to 0. Okay, so that means ly minus lambda omega x y equals to 0 is given. Now this is the standard form of SLP, Sturm-Liouville problem, where we have this part as the self-adjoint operator. Now let me introduce few notion regarding these functions, this px function, qx function, and omega x function, which is known as weight function. This is known as weight function. These functions are all real valued function. Okay, these are all real valued function, and this omega x, it is always we are considering as greater than 0. This is one important property of this weight function. Okay, omega x is always greater than 0. Okay, for usual practice, we take omega x equals to 1. Okay, that we'll see through questions, we'll see. Okay. Now here another important aspect, it is regarding this lambda. Okay, so lambda, it is parameter. Okay, and it is known as, to be specified, it is eigen value for this SLP. Eigen value. Okay, very important. Okay. Now see this equation, the second order equation, and we need to have, see, two initial conditions. So two initial conditions are initial condition What are those conditions? See, alpha 1 ya plus alpha 2 y dash a equals to 0, and here beta 1 yb plus beta 2 y dash b equals to 0. These are homogeneous conditions. Okay, so here these are the initial conditions. Okay, now see, based on the nature of this condition, you have different type of problems. Okay, where obviously this alpha 1 alpha 2 beta 1 beta 2, these are all real numbers. Okay, and at least one of alpha 1 alpha 2 and at least one of beta 1 beta 2, they are not equals to 0. That means you need to have these conditions exactly. If both are 0, then obviously there is no point of having this condition or this condition. Okay, so that's why at least one of these alpha 1 alpha 2 not equals to 0, at the same time beta 1 beta 2 not equals to 0, then obviously you will have these two conditions. Okay, now there are three types. One is Dirichlet condition, another condition is Neumann condition, another is Robin boundary condition. Okay, Dirichlet condition. Dirichlet condition, if only the y values are prescribed at the initial and terminal points. Okay, and next one is Neumann condition. If the derivatives are prescribed at the initial and terminal points. Okay, and if it is mixed, then we have Robin condition. Okay, or mixed condition. That means it is combination of both y as well as y dash at the initial and terminal point. Then we have these three cases. Okay, so this Sturm-Liouville problem, along with these three type of condition we have. Okay, our main or primary objective is to investigate the eigenvalue. Just now we stated what is eigenvalue. This lambda. This will be the primary objective. Okay, so based on this idea, this is the initial setup for SLP. In the next class, we'll be taking few questions and we'll try to solve to get this lambda value, as well as there are few important properties of SLP. Those properties we'll discuss and try to validate through examples.